Projectile motion is where we are going to first kind of put these pieces together. So this is going to be a video about projectile motion. Now we have been working through a couple of different things. We looked at free fall, which is when the only force acting on an object is gravity, but we limited that to just vertical motion because we were still working in one dimension. When we got up to two-dimensional motion, we did some vector addition, and now we are ready for projectile motion. Projectile motion is one of these things that is easiest to learn kind of by doing. So this video will be followed by a couple videos that give you some examples, and those might prove to be more useful. In the meantime though, let's get the idea across. When we have a projectile motion question, these are the kinds of questions like you have something that's got some horizontal component of motion, and then vertically it's just subject to gravity. There are a couple of kinds of questions that come up with this. One looks like this. We have the cannon, and we are going to take this and launch something or other, maybe a cannonball, hopefully a cannonball, up at some angle. We'll call that our V initial, and the sorts of things that we get with projectile motion are, where does this thing land? So we do the whole problem, and we break it up into two problems that we know how to do. We are starting at some initial position, so if we call that kind of our starting point, Y initial, and we can pick anywhere we'd like to be X initial, or to be 0. So let's say this is our initial position is X equals 0. So then what we're looking for out here is our X final. Now we might have a problem where we launch from the ground and we land on the ground, and then there are some shortcuts that we can take. We might have a problem where we launch horizontally, and that's one I'll show you separately. The big thing we're doing with this is we are trying to split this into two problems that we can handle. We know how to handle a constant velocity problem, and we know how to handle a free fall problem. Projectile motion is a combination of these, so we are going to take our initial velocity vector and break it into two components. Given a launch angle, we're going to break this into a V initial X and a V initial Y, and we're going to do that with our regular vector decomposition. So this makes a right triangle, so V initial Y is going to be V initial times the sine of my launch angle. V initial X is going to be V initial times the cosine of my launch angle. And now I have both of those, assuming that I'm given the initial speed and the launch angle, which I usually am. It's pretty uncommon to get a problem that works backwards like this. So right now, I know what happens with this, and that's kind of the beauty of Physics 1, is that these are all things that you have some kind of an intuitive feel for. You launch something at an angle, you know it's going to go up, it's going to come back down. You know the faster you launch it, the farther it's going to go, and you know there is some kind of an ideal angle for launching. So these are things that we know. I'm going to take this problem and break it into two pieces, the horizontal part and the vertical part. And I like to do this using a table. So I like to list off the different variables that I've got. I can do X initial, X final, V initial, V final, acceleration, and time. I'm going to do this when I had free fall. I did this whole thing in the Y direction. When I had constant velocity motion, I did this whole thing in the X direction. And now, I suppose I'm saying, why not both? So if I'm doing this problem, I'm going to set up what I can. My X initial is going to be 0. My X final, I don't know what that is, but that's the one I'm looking for, so let me put a star by that. V initial in the X direction is just VI cosine theta. Again, usually you would have some kind of numbers with this, and in the example videos, I'll make sure to give you some numbers with that. I'm going to skip V final for a moment, skip actually all the rest of the x direction stuff for a moment. Y direction, I have some initial height. My final height, if I'm going to hit the ground, is going to be 0. I won't even say if I'm hitting the ground. I could set my initial height to be 0, and then my final position vertically would be negative yi, which is fine too. If this is, like, let's say this is 2 meters, I could say, let's have this thing count as 0, and then down here would be y equals negative 2 meters. That's completely okay. I'm not going to choose to do that, but maybe you want to. My v initial y, that's going to be v initial sine theta. Alright, now I'm going to have to actually do, well, not quite yet. My acceleration here is going to be negative g, so negative 10 meters per second squared, because all I've got is gravity. Now the pieces. Gravity pulls downward. It doesn't have any sort of a horizontal component, so as soon as this ball leaves the cannon, I have an acceleration of 0. A lot of times people really mistake this and want to say, yeah, but the cannon's got to be giving it some kind of an x direction push, right? And it is. When we do a projectile motion problem, we are not looking at the launching mechanism, and we are not looking at hitting the ground. Once you hit the ground, you've got a new force acting because the ground changes things. And then it's a whole new problem. So what we're looking at with projectile motion is if we are launching something, we are going to consider the moment after it's launched until the moment before it hits the ground. We're not going to let it quite hit. Now the speed and the angle and the position even, where this is a split second before interacting with the ground, that's where it's going to be a split second after interacting with the ground too. So all that to say, horizontally, no acceleration. Vertically, we just have gravity. V final, if there is no acceleration, and acceleration is a change in velocity, then that means our velocity can't change. In the y direction, our final velocity, we don't know. Now a lot of people really want to say 0 here because, well, it hits the ground, it's got to stop, right? And I would want to agree with you, and I would agree with you, except projectile motion is concerned with the moment after we launch up until the moment before we hit the ground. We haven't come to a stop yet. The time, we don't know how long this thing is in the air in the x direction, but however long it's in the air in the x direction, that's how long it's going to be in the air in the y direction. So these two are going to be the same as each other, which will make this feel a lot like a pursuit problem. So that's the basic setup, and then I'm going to jump to my same equations that I always use for any of this constant acceleration business, and I do have a constant acceleration in both directions. In the x direction, my acceleration is 0 and constant, which is really easy. In the y direction, it's gravity and constant. So then I'm going to use my equations. My first equation is going to look like x final equals x initial, v initial t, half at squared. And anywhere where I've got an x, I can substitute in a y. I'm going to have a final speed, final velocity, based on initial velocity. And then if I take this second equation, solve it for t equals, plug it into the first equation, and do some rearranging, I would get this equation. It's an acceleration. Just like before, I am defining these equations based, or identifying these equations, I suppose, based on what's missing out of them. This first equation does not have a v final. Second equation does not have any information about position. And the third one avoids time. When I do a projectile motion problem, I can pretty much guarantee that that's my initial setup. It will be the vast majority of the time, maybe every time. The other last piece, promise, in the x direction, my acceleration is 0. When my acceleration is 0, this part of my equation goes away, this part of my equation goes away, and this part of my equation goes away. That first equation, I still have something to work with. The second equation, v final equals v initial, yeah, it's true, and I've already got that here. It's true, it's just not helpful. And the third equation, v final squared equals v initial squared, is also true, but not helpful. So when I do a projectile motion question, and I'm trying to figure out, I've got my setup, I've got my table, and I've got my tool belt of 3 equations to work with. If I'm working with that x direction information, equation 1 is pretty much the only way I'm ever going to go. And I get the shortened version of equation 1 that doesn't have this last term in it. It's just the constant velocity portion, which makes that a nice place to be able to start. Hopefully that's enough to get you moving with this, to get the idea going in your head, but the next couple of videos will be examples that work through it.